How are we doing today? Today we're moving on with our solution talk with concentration, and today we're going to focus on parts per million. Last class or last set of notes was about molarity. This is just a different way to express concentration in a numerical form. This is a formula, shall we say, or something that's used kind of widespread outside of the world of chemistry. So you'll see parts per million or sometimes parts per billion when you read articles or watch news reports on various things. So it's something that it's good to be familiar with. Okay, first question. Explains in terms of polarity if carbon dioxide is soluble in water. So this should be a review thing from our polarity unit or our bonding unit. Water, hopefully you remember water is a polar molecule. Carbon dioxide, if you remember, it's that straight molecule with carbon double bonded to two oxygens. So you end up with that linear shape. So it's symmetrical. So that makes it nonpolar. So carbon dioxide and water are one's nonpolar, one's polar. So they're not the same. So they're technically not soluble in one another. Think of soda. I use carbon dioxide and water a lot because soda is something everybody kind of is familiar with. Soda does not stay carbonated unless it's in a pressurized container like the can or the bottle that it came from. As soon as you open it, it's going to lose the carbonation, and it'll lose it fairly quickly in a relatively, couple hours if it's left completely wide open. Even in a bottle, it will lose carbonation once it's been cracked open because you can't seal it completely tight. Okay, so that's this like dissolves like review. Table F, I want to refresh this again. Remember, left side makes solutions, right side does not. And when you're looking for these things, you have to find one part of the compound. So, whether, let's say you have the compound calcium chlorate. All right, calcium. It's hard to look up an individual element, but you have to recognize that calcium is a group 2 element, so it's not group 1. It's not ammonium. It's not nitrate. It's not acetate. It's not hydrocarbon. It's not chlorate. It's not perchlorate. It's not halide. It's not salt. So calcium's not listed here. Calcium's not listed over here either. But chlorate is. Chlorates are listed right here. There's no exceptions to any compound bonded with a chlorate is going to be soluble in water. All right, and then you could do the same thing over here. Calcium hydroxide. So hydroxides generally are insoluble except when combined with calcium. So in that case, calcium hydroxide is soluble in water. All right, so we've seen this chart now 3 or 4 times this year. You should be becoming fairly familiar with it. Okay, properties of liquid solutions. So everyone has problems, but chemists have solutions. Haha, joke of the day. Okay, so liquid solutions, these are, usually it's 2 liquids mixed together. Sometimes you can get a solid mixed into a liquid like Kool-Aid. All right, but they are homogeneous. By definition, a solution is homogeneous, which means it's uniform throughout. Solutions by definition are clear. All right, so that means they're transparent. So you can see through them. All right, think of Kool-Aid. Even the colored Kool-Aids, you can see through all of them. You can't see clearly, all right, but they are transparent. You can see an object on the other side of them. They can have color depending on what's in the solution. So, just being clear is not a property of a solution. All right, a property of a solution is if they are left alone, it won't settle out. It won't collect at the bottom. So they will not settle out if they're left alone. All right, and you cannot separate the components of a solution by using filter paper or any type of filter for that matter. Whether, think of a cartridge filter for your pool, or even a filter for your sink or your refrigerator, the water that comes into your refrigerator. All right, that's not going to remove any solute particles that are in solution. It could remove some minerals. It could remove some big particles. All right, but the particles of a solution are too small. All right, so there's no filter that's going to remove those particles of the solution. All right, rate of solution formation. So how quickly a solution is formed. So I say how much over time. We'll talk about rate in the next unit in equilibrium, but right now rate is it's essentially time. All right, it's not a time unit, but it's a way to measure it. All right, so how much will dissolve or how quickly will dissolve it does have an impact on how much solute is already dissolved. All right, so if it's close to saturation, all right, it's going to dissolve slower. Okay, so if it's just a solvent and you add a little bit of solute, it's going to dissolve really quickly. If you have a solution or a solution that's almost saturated, There's not a lot of space for that solute particles to go. So it just takes time for it to find it. So it takes a little bit of time for it to dissolve. All right. You can increase the solution formation by stirring. All right. That's going to increase the collisions between the solute and solvent particles. All right. Which is going to increase how fast it will dissolve. Stirring does not have an impact on how much will dissolve, though. It only increases how quickly it will dissolve. All right. Increasing the temperature, all right, that will allow the collisions between the solute and solvent particles to occur quicker, which will increase its solubility rate, formation rate. It will also increase how much can dissolve too. So that's kind of one of those ones that goes both. And then the particle size, we kind of talked about this. You have the big block of salt, you have the granulated salt. The granulated salt will dissolve much quicker than the big block of salt because you're increasing the surface area. That's what SA is on here. So SA right here means surface area. So if you decrease the particle size, which means you increase the surface area, that means it's the greater likelihood that solvent and solute particles will collide, which means they'll dissolve quicker. Okay, parts per million formula. This formula is on your reference tables. It's on the concentration section in the back. Last class, we talked about molarity, which means moles per liter. All right, parts per million is massive solute over massive solution. Now, one thing you do want to remember about the solution, though, is the solution is comprised of the solute and the solvent. So you do have to add both parts of the solution in there. Okay, so that's something that's important, especially in like a part 2 type question where you have to show your work. If you forget to add in the solute, which happens frequently, you can't get full credit for it. So just be careful of that. So that's the parts per million formula. And then you multiply that by 1,000,000. If it was parts per billion, you just multiply it by 1,000,000,000. It's the same formula, same process. It's just taking it out to a different factor to make the numbers easier to say. So yeah, usually parts per million numbers are like in the ones, the tens, or the hundreds number. You try not to get really small numbers or really big numbers. Okay, example problem number 1. So here we go. We got an Olympic-sized swimming pool. CNS is still working on a swimming pool. But if you've ever been to an Olympic-sized swimming pool, they're really big. All right. So we're going to say approximately they contain 2.5 million liters of water. Okay. So if you dissolve 1 teaspoon of salt in that pool, what's the concentration? All right, and that's what we're asking for. So 1 teaspoon of salt, I'm telling you, has approximate mass of 6.75 grams of NaCl. So from here, you have all the information you need to solve the problem. So first things first, you're going to want to get your formula, parts per million, massive solute over the massive solution times 1,000,000. So the solute in this case is the sodium chloride. So they're telling you they're only putting 1 teaspoon in, 1 teaspoon of 6.75 grams. So that's their top. The bottom, which is the solution, is somehow we have to get a mass of this. All right. Now, we know the density of water is 1. All right. And density units are grams per milliliter. So the density of water is 1 gram per 1 milliliter. So that tells me every 1 milliliter of water is equal to 1 gram. All right. So 1 milliliter water has a mass of 1 gram due to the density. That's what I say right here. So we have to take this number and convert it to milliliters. So if you remember liters to milliliters, liters is the base unit, milliliters is 3 places to the right. So you can just multiply it by 1,000, or if you do dimensional analysis, or you remove the units, all right, you've got milliliters, 1,000 milliliters is equal to 1 liter. So in this case, you end up multiplying by 1,000. So you get 2.5 times 10 to the 9. Now you can write out 2, 5, and then 8 zeros, but it's way easier for me to type that number. So that's the mass. So this is the milliliters of water. And we know that 1 milliliter is 1 gram. So the grams of water is going to be the same thing. So it's the 2.5 times 10 to the 9 grams plus the mass of the solute, which in this case is 6.75 grams. So you got to add those up, divide 6.75 by that sum, and then multiply by 1,000,000. When you do that on your calculator, I think I can move this. There we go. You get 0.0027 parts per million of sodium chloride in the pool. That's from 1 teaspoon of salt in that pool. All right. So that's why this parts per million unit comes in handy for things that are really low concentrations. All right. So I'm not going to go through multiple problems of this. I'm going to give you some problems for homework to do. So I don't think keep going through this, it doesn't really help in this world, this format that we're in. So factors affecting the amount of solute. So in the beginning, we talked about the rate of solution formation, which didn't really change how much was dissolved. Now we're going to talk about how we can change how much is actually dissolved. So temperature. All right, increasing the temperature will increase the solubility of all solids and liquids. All right, I say most here, but it's really all. Increase the temperature, gases become less soluble. All right, so solids and liquids are going to become more soluble at higher temperatures. Gases will become less soluble. That's that table G. Remember the three things that go down, those are all gases. Pressure only affects gases. So if you increase the pressure, it increases the pressure or increases the solubility of the gases. If you have a solid dissolved, changing the pressure is not going to have any impact about it. I tell you to think about soda here. When it's packed in its original container, there's a lot of pressure on it. You open the cap, that pressure is released, and then the CO2 starts to come out of solution. I guess I didn't do the animation on this. Anyway, so we'll stop here. That's fine. It's just a review molarity problem, but that's fine.